So yeah, how are traps formed? Okay, I just said that. Traps are formed when rocks are deformed or when their quality becomes altered in a manner that creates, arrangements suitable for housing hydrocarbon. In defining, or in evaluating traps, a few things that we normally think of. I talked about timing. That's very critical. That's very important. Okay, so the timing of initial deformation is key. The nature of the rock material. When I mean nature, I'm talking about the mechanical property of the rock, the elastic property of the rock, the surrounding, the overburden or the sealing rocks around. What's up with these rock materials? And then the history, not just timing on nature, but the history and sequence. In fact, that's very key. In basins of the world where you've had polyphase deformation, you realize that it's not just about knowing what happened at one time stamp in the past, what happened at a particular time in the past, but what happened thereafter. That's actually one element that will help you figure out things better in terms of de-risking your trap integrity, in terms of better understanding of whether the trap is working or not. So why do we care as subsurface scientists, as subsurface engineers? We want to, of course, we care because a detailed understanding of the impact of local and regional tectonics, helps us figure out which areas of our basin we expect the traps to work or not. And even for each of those different, domains in a particular basin, it gives you a better picture of what do I expect in terms of risking. Okay, so regional knowledge is very key. So as an explorationist or as someone who is moving into a frontier basin, you already have an idea of what do I expect because of that knowledge of that regional setting. I already talked about risk. Of course, it helps you understand in terms of, in the spatial sense, what risking to expect in the different domains of your assets. If I go to this area of my asset, what do I expect? Do I expect to see more of pop-up structures or trusted anticlines, or what do I expect to see? And then what risk is associated with those kind of traps? Even before you move in there, you already have an idea. Of course, it also helps you because as geoscientists, as subsurface engineers and scientists, we are interested in finding the big traps, the low risk, volumetrically robust traps. Of course, that's what every one of us will like. We want to find out the best opportunity that will give us the least amount of technical and production or drilling risk. So that's why we care. So if we move on a little bit to something a little different, timing of initial deformation. I'll start with faults, and then we look at that piece of discussion for food. So for a start, just imagine it's very simple, normal fault systems anywhere in the world. Let's say in this case, we have two layers A and B, and we have two faults, fault 1 and fault 2. So the question here is, I know you probably know this, but we need to still go through this. When did these individual faults form? Now, the simple thing to do is to look at the thicknesses on both the hanging wall and the foot wall. So in this very case, the layer A is deposited during the Miocene, and that of layer B is Pliocene in age. So what you see, if you take a closer look, is that as you go from the foot wall, that's, let's focus on fault 1 for now. As you go from foot wall to the hanging wall, you see that there is, thickening across the fault plane for the layer A. But if you focus on layer B, you don't see that change in thickness. So what this is telling us is that at the time, this fault 1 was active at a particular time when the fault layer A was being deposited, and that was during the Miocene. And that fault had healed, meaning it wasn't active during the second phase, which was when the layer B was being deposited. So layer B was actually deposited post kinematic of that fault 1. So if we consider fault 2, again, what you see is that if you're going across A across the fault 2, if you go across the fault plane, we don't see significant changes in the thickness. In all of this, we're assuming no erosion. We're assuming that the thickness is just as is in the original sense. Nothing has been eroded. That's, okay, I should have said that earlier on. So if you, again, if you look at the layer B, you see that across the fault 2, you see thickening. That tells us that that was when that false 2 was active. So in other words, false 2 was active during the Pliocene period. That meant that the faulting happened while the layer B was being deposited, and obviously we see that from the thickening, from the thicker component that we see on the hanging wall. So if we, in a similar sense, if we focus on folds for now, what you'll see is that there are 4 layers here, 1, 2, 3, and 4. So what we notice here is that for layer 1 and 2, you don't see significant changes in its thickness on both limbs of the fault of the fold, and but for 3 and 4, we see that there's some kind of thinning onto the crest of the structure. Now, if we imagine that in terms of age, the layers are Eocene, Oligocene, Miocene, and Pliocene for 1, 2, 3, and 4 respectively. So that tells us that if you look at 1 and 2, because we see that it's isoparcous, in other words, the thickness is about the same, on both limbs of the fold. It tells us that that was when this area wasn't active. There wasn't any compressional movements happening. So that means that that was more like a quiet phase in terms of the structural sense of things. But between from the time 3, that's from the Miocene to the Pliocene age, obviously we had some kind of structuration happening, because we see that because we see that there is thinning onto the crest of this folded structure. So in terms of timing, we'll say that this structure was active. The onset of this fold was maybe sometime in early Miocene, and that continued to the Pliocene periods as we made that call by looking at the thickness of this of the strata on both limbs.